Welcome to The Explainer. Today, we're going to break down the incredibly complex world of cancer. We're going to look at how just one single healthy cell can go rogue, kicking off the uncontrolled growth that defines this disease. And, how understanding these tiny building blocks is changing absolutely everything. All right, so here's our game plan. We're starting at the very beginning with a genetic glitch that actually sparks a cancer. Then we'll get into how doctors describe a tumor and how it spreads. We'll also cover how it's tracked through the body, and then we'll wrap it all up by putting the pieces together with a really interesting case study on breast cancer.
To really get a handle on cancer, you have to start small. I mean, really small, down at the level of our DNA. So let's look at how a single, perfectly normal gene can just go off the rails and set this whole chain of events in motion. Okay, so inside every one of your healthy cells, you've got these genes called proto-oncogenes. You can think of them as the super responsible managers of cell division. Their whole job is to make sure everything happens in a controlled, orderly way. They are absolutely vital for keeping our bodies running smoothly. But here is where the problem can start. If a mutation, a little genetic glitch, hits that proto-oncogene, it can morph into something called an oncogene. Now, an oncogene is basically like a car's accelerator pedal, getting slammed to the floor and stuck there. The go signal for cell division is now just permanently switched on. Now, the really crucial thing to get here is that this isn't about the cell losing a function. It's about it gaining a dangerous new one. This gain-of-function mutation gives the cell this new superpower to just ignore all the normal stop signs, letting it multiply over and over and over, forming the very beginning of a tumor. So, once a tumor has actually formed, doctors need a way to talk about it, to describe it, and they use two key terms that sound kind of similar but mean totally different things: grading and staging. The simplest way to think about it is like this. Grading is all about the cancer's character. How weird and aggressive do the individual cells look? Staging, on the other hand, that's about the cancer's footprint. How big is it and where has it traveled in the body? And this gives us a fantastic peek into what a pathologist sees down a microscope. You've got the normal cells, all neat and orderly, but then you see the cancer cells, and it's just chaos. They're disorganized with these bigger, darker nuclei. That visual difference, that is the very basis of how they grade a tumor. And this grade is put on a pretty simple scale. Grade 1 cells, well, they still look a lot like normal cells. But by the time you get up to a grade 3 or 4, they look really different, and you'd expect them to be much more aggressive and grow a lot faster. Okay, now for staging. And this is one of the most critical factors for figuring out a patient's prognosis and their treatment plan. The universal language that doctors all over the world use for this is a system called TNM. So the TNM system just breaks it all down. T is for the size of the main tumor, N tells you if it has spread to nearby lymph nodes, and M, that's for metastasis, has it traveled to distant parts of the body. Doctors then combine these scores to give an overall stage, from stage I for a small, contained cancer, all the way to stage 4 for a cancer that has spread widely. Right, that M for metastasis is probably the most important letter in the whole system because a cancer spreading is what makes it so incredibly dangerous. So how in the world does a cancer cell manage to pack up its bags and travel through the body? And to really get why this matters so much, just think about the staggering number for a second. Around 90% of all deaths from cancer aren't actually caused by the original tumor. They're caused by metastases, those secondary tumors that pop up after the cancer has already spread. And this whole process is a wild journey. First, a cell has to actually break free from the tumor. To do that, it goes through this transformation, basically changing from a stationary cell into a mobile one. Then it hitches a ride in the blood or lymph system. And to start a new tumor, it has to reverse that whole process, settle down in a new spot, and start growing all over again. It's pretty incredible. So, if cancer has this amazing ability to spread, how on earth do you track it? You can't always see it on a scan. Well, that's where something called tumor markers come into play. So while they're not always the best for making that initial diagnosis all by themselves, tumor markers are incredibly valuable for tracking the disease. They can tell doctors if a treatment is working or if a cancer has come back, sometimes way before any symptoms show up. These markers are basically substances, usually proteins, that are shed by cancer cells into your bloodstream. They act kind of like a signal flare. So, for example, high levels of PSA might signal prostate cancer. while CA-125 is linked to ovarian cancer. Doctors can measure these levels with a simple blood test and just watch them over time. All right, so let's see how all of these building blocks, the genetic glitch, the staging, the tumor markers, how they all come together in a real-world scenario, a very specific type of breast cancer. So triple-positive breast cancer gets its name from 3 key markers found on its cells. It has receptors for the hormones estrogen and progesterone, which means they act like fuel for its growth. And it also overproduces a protein called HER2. Now, remember that proto-oncogene we talked about, the one that can get stuck in the on position? Well, the gene for HER2 is one of those. So when it's overactive, it's just like that stuck accelerator pedal driving all this uncontrolled growth. These 3 markers tell us exactly what's feeding this particular cancer.
And because we can identify these specific markers, it allows for a highly personalized attack plan. Doctors can use endocrine therapies to block the hormones. They can use targeted drugs like trastuzumab to specifically shut down that HER2 protein. This kind of targeted approach, often mixed with chemo, has totally transformed the outcomes for these patients. So the real takeaway here is this. By understanding every single piece of this puzzle, from that first tiny genetic glitch that creates an oncogene, all the way to the specific markers on a cell's surface, medicine can now move beyond a one-size-fits-all approach and design much smarter, much more effective treatments. And this all brings us to a final, pretty provocative question. We are clearly stepping into an era of truly personalized oncology. As our map of cancer's building blocks gets more and more detailed, you have to wonder, how soon will it be until every single cancer treatment is as unique as the patient getting it? The fight is fundamentally changing, one patient and one genetic glitch at a time.